Today you're going to talk about the ideas of direct and inverse variations. Now in Algebra 1, you spend some time looking at linear functions and how to write them and graph them, etc. But we haven't quite discussed yet the notion of variation, meaning how the two variables that you are showing the relationship between are changing in relation to each other. When a situation is modeled by a linear function that's in the form f of x equals kx, or better yet, y equals kx, k is considered a non-zero constant. We say that there is a direct variation between the variables. So in other words, as y goes up, x goes up. As y goes down, x goes down, meaning they both go in the same direction. And the ratio of y to x remains constant, hence the linear function. In the case of y equals kx, sometimes we'll describe this as y varies directly as x, or y is proportional to x. And the number k, now I know it's strange that we call it the number k, but remember this is a constant, meaning it is a number. We call that the variation constant, or the constant of proportionality. We sometimes also call it the constant of variation. The constant of variation. So you'll hear three different ways of describing this same thing. The constant of variation tends to be what I use, variation constant, or again, the constant of proportionality. All three of those things are used to describe the letter K in our variation scenarios. So let's see if we can write some direct variation equations for each of these scenarios. Remember, it's always going to be in the structure y equals kx, k times x, where y and x are the variables that we are showing the relationship between. So, for example, in number 1, it says area varies directly as the square of the radius. Okay, so we're going to call area A equals, varies directly, so we know we're going to have k times the square of the radius. That would be r squared. So the equation of variation for this scenario would be A equals k times r squared. Let's try another one. State income tax is directly proportional, okay, to gross income. So let's start with state income tax. Let's call that S equals, now it's directly proportional, so we're going to have K times gross income, maybe we'll call that G. S equals K times G would be the variation equation for this scenario. And how about one more? Hooke's law. This is a pretty famous law from physics. It says the distance a spring stretches varies directly as the force on the spring. So the distance, d, is equal to, and this is a direct variation, so there's that k again, that constant of variation, k times the force on the spring. The force on the spring. So d equals k times f is the equation that we're looking for here. Once we've established the variation equation, the direct variation equation, then usually what we need to do is we need to find the value of that constant. We need to find k. So it's just a matter of manipulating whatever the variation equation is to isolate k. And that tends to be the first thing that you're going to do in situations. Let's take a look at how we use direct variations in algebra. Let's look at the example on the page here. The distance a ball rolls down an inclined plane is directly proportional, there's that directly proportional piece, to the square of the time it rolls. Okay, so let's start by step number 1, write the variation equation. So we have the distance that the ball rolls down an inclined plane is directly proportional to, so that was equals k times, the square of the time that it rolls. So that would be times t squared. Now we can use this because the next part of the question says, during the first second, the ball rolls 8 feet. How far will the ball roll during the first 3 seconds? All right, so we've got the variation equation here. The next thing we need to do is step number 2, find the value of the constant of proportionality. So we're going to take our d equals k times t squared equation, and we're going to isolate k by dividing both sides by t squared, and that's going to leave me with d divided by t squared is equal to k. So d divided by t squared is equal to k. Now, let's substitute the values that we know from the given scenario. That's this piece right here. During the first second, right, that would be t equals 1. The ball rolls 8 feet, so that would be the distance. We have k equals 8 divided by 1 squared. 1 squared we know is 1. 8 divided by 1 is 8. So our constant of proportionality, k, is equal to 8. That's really useful because that 8 then can be used in our direct variation equation for k, right? We just want to remind you, we just found the value of k. We can use that 8 to help us find any other scenario of that same ball. It says, how far will the ball roll during the first 3 seconds? So how far will the ball roll? It's asking us to find d. D is equal to the k, which is 8, times the first 3 seconds. That's our time, t. That would be 8 times 3 squared. 3 squared is 9. 8 times 9 is 72. 72. And because this is a scenario that has real numbers and real units, we need to make sure we put the units on what we just found. The distance, right? Distance was 72 feet. We just look back at our equation and we can see, or our problem, we can see that our distance is measured in feet. So in the first 3 seconds, the ball will roll 72 feet. One more time, what we did was we rewrote the variation equation based upon what it told us was directly proportional. Then second, we found the constant of proportionality by isolating the k in that equation. And then in step number 3, we substituted that given value for k and the value of the variable that it gave us to find the missing variable. Let's look at a couple more examples of direct variation. Here's another example. If y varies directly as x, let's just go ahead and put down that direct variation equation, y equals k times x, and y equals 32 when x equals 2, so there's the information we're given, find the variation constant and write the equation of variation. So, it's first thing it says is find the variation constant. That would be k. And again, to solve for k, all we do is divide both sides by x, and we get y divided by x. And since y is 32 and x is 2, 32 divided by 2 is 16. So our value of k is 16. The second part says, write the equation of variation. Well, that's simple because all we need to do is rewrite this initial equation, but substitute k in for 16 in for k. So we get y equals 16 times x, or y equals 16x. This is called the variation equation or the equation of variation. Let's try some more. These do get a little wordy, so please take your time and read them carefully. It says, the speed v of a train of ocean waves varies directly as the swell period t, or time between successive waves. So right there in that first sentence, we can go ahead and we can write our variation equation with k. So the speed v of a train of ocean waves varies directly, so that would be V equals K times the swell period, or T, the time between each wave. With this equation, we can then isolate K to solve for our variation constant. That would make K equal to V divided by T. Remember, we're just dividing both sides by T to get K by itself. Let's look at the second part of this problem. It says waves with a swell period of 12 seconds. Remember, that's our T, are traveling at 21 miles per hour. That's our V. So we have 21 mph divided by 12 seconds. All right, we're going to do 21 divided by 12, and we get 1.75. That's our constant of variation. Now we're going to use that K. So again, we're going to substitute that K back into our original equation, and we're going to solve for the unknown thing. It says, how fast? That's our question. How fast? I think it wants us to find V, right? How fast are waves traveling that have a swell period of 20 seconds? So V is equal to K times T. K is 1.75. T, we know, according to our problem, is 20. And 1.75 times 20 is 35. So 35, and our units here on velocity are miles per hour. I did want to take a second and just remind you that when you're writing equations and you're using numbers in those equations, we do need to make sure that our units remain the same. For example, if in our original K, finding K, our velocity was in miles per hour, we do need to make sure that our velocity in the last part is also in miles per hour. And if the time was in seconds, we need to make sure the units stay in seconds. There are times when you're going to have to do a small unit conversion from like miles to kilometers, or minutes to seconds, or hours to minutes, or something like that. Keep that in mind. We should probably make note here on our notes to keep the units consistent. Okay? You're always going to have to be on the lookout. Then sometimes the numbers they give you have units that are not consistent, and you need to make sure that they are. We're going to do one more. Let's look at this last one here. The rate of change R of the temperature of an object is proportional. Remember, that's the same thing as saying directly proportional to. R is directly proportional to the difference between the temperature of the object and the temperature of the environment. Whoa, the difference between them. So remember, that would be, let's see, the rate of change R is directly proportional to times the difference between T and T sub E. Aha. So we can find K by doing R divided by T minus T sub E. Let's see what information they give us. If an object's temperature changes 12 degrees per minute so that would be R, when the difference in temperature between the object and environment is 8 degrees, how fast would the object cool if the difference in temperature was 20 degrees? So in other words, they want us to find R, but first we need to find the value of K. So we're going to do 12 divided by 8, and we're going to get 1.5. And then we're going to use that 1.5 as our K. All right, so we're going to do R equals 1.5, and then the difference in temperature was 20, and R 1.5 times 20, it gives us 30. So the rate of change of our temperature is 30 degrees per minute. That's direct variation. We will find another video on inverse variation and joint variation in just a little bit.